Hello students, welcome back to Vassiversity. Today we're going to be talking about rates of change. Alright, so let's recall the definition of the derivative. So we had delta x, right, which was the change in the x component. So x2 minus x1, and delta y, right, which is f of x2 minus f of x1. Right, when we take a ratio of delta y to delta x, so delta y over delta x, we get essentially a difference quotient, right, which is, in other words, called the average rate of change. So f of x2 minus f of x1 over x2 minus x1. Right, if we approach delta x to 0, we will end up getting a derivative, right? And so graphical representation, remember when we were doing the derivative a few lessons back, we had this graph right here. So we had a slope of a line, right? So we have a point P, we have a point Q. So essentially, the rate of change is the line between point P and point Q. Okay, so the average rate of change of y with respect to x over the interval x1 to x2, right here, is, and it can be interpreted as the slope of the secant line. Okay, so if we say delta x, so if we say limit as delta x approaches 0 of delta y over delta x, that will actually be equal to dy over x. All right, so that is the derivative. Okay, so that is the derivative. So it's exactly at the point that we're trying to evaluate. All right, so some of the applications of this of their average rate of change can be seen in physics. All right, so let's go ahead and take a look at the first problem. So here's going to be first example, right? So the position, right, of the particle is given by the following equation, right? S is equal to f of t, where t is the time, t cubed minus 6t squared plus 9t. So where t is measured in seconds and s is in meters. So part A is find the velocity, right? So, well, we know the velocity is position over time, but we want to find it at any moment of time. So velocity, v of t, is actually going to be ds over dt. So it's going to be the derivative of the position, right? Which is, to be more exact, right, it will be, so d dt of f of t, right, by using the power rule, we will get 3t squared minus 12t plus. Okay, then we want to find the velocity after 2 seconds and after 4 seconds. So, okay, we will go ahead and evaluate the function that we found in part A. So v of 2 is going to be equal to 3 times 2 squared minus 12 times 2 plus 9. Right, if we evaluate, we're going to get negative 3 meters per second. All right, and then at 4 seconds, e of 4. So we're going to have 3 times 4 squared minus 12 times 4 plus 9, which will be equal to 9 meters per second. All right, then when is the particle at rest? All right, so the particle is at rest when the velocity is 0. So we're trying to find v of t to be equal to 0. Alrighty, so let's go ahead and write it down. So we will have 3t squared minus 12t plus 9 is equal to 0. Right, so we are able to factor some stuff out. So let's go ahead and do that. So we can factor out 3. 3 times t squared minus 4t plus 3 is equal to 0. Alrighty. Then, so we can factor out, so we can divide both sides by 3, and then we can factor out, because here we can have 2 factors. So we're going to get t minus 1 times t minus 3, which is equal to 0. So that means that the velocity is 0, so the particle is at rest when t is equal to 1 and t is equal to 3. Right, and both of them are greater than 0, so both of them are valid. So we're going to say that at t equal to 1 second and t equal to 3 seconds, the particle is at rest. All right, part D. When is the particle moving forward? That is, in the positive direction. All right. So the particle moves in the positive direction when the velocity is positive. Right, that makes sense. So moving forward implies that v of t is greater than 0. Right, so what does that mean? That means that 3t squared minus 12t plus 9 is greater than 0. So we know we already factored out previously. So we will have t minus 1 times t minus 3 to be greater than 0. Okay, so we know, right, we want to find when does this inequality holds true. So this inequality is true when both factors are positive. So essentially t is greater than 3, right? So that implies that t gotta be greater than 3. Okay, or when both of them are negative, right? T is less than 1. So, okay. So essentially, but the time is greater than 0. So we're actually know that the particle is moving backwards So the particle is moving backward between 1, t, and 3. All right, so other than that, it's going to be moving forward. Alrighty, perfect. Then part E, we want to draw a diagram. Right, we want to draw a diagram represent the motion of the particle. So, well, we can use the information, right? So from the previous parts, and essentially, for part E, right? For part E, we would get a graph like this. Perfect. So that would be a representation. So using the information from part D, we can make x, the motion of the particle back and forth along a straight line. Okay. Then part F. Find the total distance traveled by the particle during the first 5 seconds. Okay. So because of the things we learned in part D and E, we need to calculate the distances traveled during the time intervals from 0 to 1, 1 to 3, and 3 to 5 separately. Okay, perfect. So let's go ahead and start with the first interval, 0 to 1. So we're going to have distance, so between f of 1 minus f of 0, which is going to be 4 minus 0, which is equal to 4 meters. Then the interval between 1 to 3. Okay. So we will have distance between f of 3 minus 1, So that's equal to 0 minus 4, which is equal to 4 meters. Okay. And then between 3 to 5. So we're going to have f of 5, 3, which is equal to 20 minus 0, which is equal to 20. So the total distance is going to be equal to, 4 plus 4 plus 20, which is equal to 28. Righty. And then the last part is find the acceleration at the time t and after 4 seconds. Okay. Perfect. So for g, we know that a of t, which is acceleration, is equal to d2s squared, so second derivative of the position, which is the same thing as the derivative of the velocity. All right, which is equal to 6t minus 12. Right, so this is our general formula. And we want to evaluate it at 4 seconds. So we're going to have 6 times 4 minus 12, which is equal to 12 meters per second squared. Righty. And, well, we can also go ahead and graph all of the 3 functions. So we can graph position, velocity, and acceleration, right? Position, velocity, and acceleration. Acceleration is going to be linear in distance. Right? Perfect. Perfect. So this is one of the examples of physics that we used, right, in order for us to solve some problems. Now we can go ahead and take a look at another example, right? We can take chemistry. So for example, if we have the following. So, a chemical reaction results in a formation of one or more substances from one or more starting materials, right? So let's consider an equation, a chemical equation. 2H2 plus O2 will produce 2H2O. Hydrogen plus oxygen will produce. All right. So indicates that the 2 molecules of hydrogen and 1 molecule of oxygen form 2 molecules of water. So, right, what we can do, essentially, by using the rate of change, we can talk about the concentration of the material that we have. Right, so let's consider the following equation. So let's consider A plus B goes into C. Right, where A and B are essentially reactants, which are the starting material, and C is the product, which is the substance that we get after the reaction. Okay, so the concentration of the reactant A is the number of moles. So moles, 1 mole is equal to 6.022 times 10 to the 23 molecules, called an Avogadro's number. Okay, per liter. So moles, so essentially the concentration is moles per liter. So per liter, the concentration. Right, and essentially the concentration varies during a reaction. So we're going to label concentrations as bracket A, bracket B, and bracket C. Okay, right? So, and they all function of time, right? As time passes, the concentration changes. So the average rate of a reaction of the product C over time interval is going to be as following. So it's going to be delta concentration of the product over delta time is equal to, so concentration at the time t2, right, minus concentration at time 1 minus, over T2 minus T, right, which is a standard average rate of change, right? But as a chemist, we would be more interested into the instantaneous rate of the reaction, which is obtained by taking the limit, right? So if we go ahead and take the limit, right, limit as delta T approaches 0, okay, we would essentially end up with d of the concentration over dt, right? And in real life, you essentially you can get the function, right? You can get the function by getting the data, by getting the actual physical data on hand and analyzing it and building up essentially the function that will describe the physical results, right? And of course, it's always good to have initial function to have a baseline to start your experiment with. Okay, so since concentration of the product increases, right, as the reaction proceeds, the derivative will be positive. Okay? So the rate of the reaction is positive. So, but however, the concentration of the reactants, right, will be decreasing, right? Because if we're spending the material that we started with, we're going to be decreasing. Meanwhile, we're going to form the product. Okay, so an interesting thing we can develop from this. So a rate of reaction in chemistry, rate of reaction is essentially, we're assuming that it's, it's exactly the same across all of them. So, but it's going to be d of the concentration, dt, which is positive, which is going to be the same thing as negative concentration of a element, of a reactant, and it's the same thing as negative derivative of the B reactant. Okay, and so more generally, right, there are more general form of this, right? So general form, that would be, so if we have an equation, right, if we have an equation like this, so coefficient A, so number of, right, molecules, plus B times B produces C times C plus times D. So the general equation becomes -1 over A dA dt, which is equal to -1 over B dB dt, which is equal to +1 over C dC dt, and 1 over D of concentration of D over dt. So, and in chemical theory, the reaction, right, based on the reaction, based on the materials and the way the reaction is proceeding, there are equations, there are baseline functions of time that would describe a reaction equation, right? A reaction equation, so you can actually get more of an analytical function rather than based off the data, right? And of course, as I said, it's going to be more of the baseline to compare the results, and then the actual data will be the one that adjusting the function that you end up getting. All right. So, of course, we can also do some biology with it, right? And biology is extremely famous for the predator and prey problem, for the growth population, for a lot of dynamical systems, right? We call it dynamical in mathematics. So everything that requires multiple entities present will be a system, right? So we're going to take a look at a very simple example. It's going to be the rate of growth, right? The rate of growth. So, let's go ahead and do always. So biology. So we can say, well, let n to be f of t, right? It's essentially the number of individuals in animal or plant populations. Number of individuals individuals in animal or plant population, right? So it's number of individuals in population in general. Plant population at time t, right? At time, right? So the change in the population size between times t1 and t2, right, would be delta n, which is equal to f of t2 minus f of t1, right? And so the average rate, right, the average rate would be delta n over delta t, which is equal to f of t2 minus f of t1 all over t2 minus t1. Okay, so if we take a limit of it, right, if we go ahead, this is average, right, average rate, right, if we want to get an instantaneous rate of change, or we also call it the growth rate, right, it will be the limit as delta t approaches 0 of delta n over delta t, and that would be the derivative of n back to t. So essentially, this is, it's not very accurate because the population would be a step function whenever the birth or death occurs, right? So therefore, we cannot really differentiate it. But for a large animal or plant population, we can replace essentially by approximation, right? So if we have a small population, right, we essentially would call it discrete, right? Meanwhile, if we have a big population, we would call it continuous. So scientists study both discrete and continuous systems, right? Because they both give different perspectives onto the things that are happening. So, all right. So, for example, right, we would analyze the growth population, something like this, right? We would approximate it with the line, right, the smooth line. Meanwhile, the population growth, right, every birth would be a step size, right? It's essentially a step size for time, right, for some time. So this number is constant until a certain time, until it jumps again or it drops again if this has died. Okay, so to be more specific, like if you consider a population of bacteria, right, also very common in bacteria. So what can happen is, let's say if we take a look at the bacteria, we might have something like, a time after 1 hour, we have 2 times the initial condition, right, which is 2 times n naught. Then after the second hour, right, we have twice as much as the first one, which is 2 squared times n naught, right? And then the third hour, we have 2 of the second hour, right? So it's 2 to the third. So if we continue right after n hours, we can get a function actually, f of t, for the bacteria growth, which is going to be 2 to the power of t times n naught. So this is the population function of the bacteria, right? Population of bacteria. Right, and we can take measurements, for example, right? If you have a microscope, you can take measurements. And the function can slightly vary, right, based on the bacteria itself, right? But for example, this is going to be an exponential function, right? And in the previous lesson, in previous few lessons, we learned how to deal with the exponential function. So we can easily take a derivative of it, we can evaluate it, we can find everything about this function, everything that we might be interested in. All right, perfect. So, essentially, last thing, of course, there's plenty of applications in engineering, and we will be doing a lot of engineering problems as we move forward. So, but the last thing I want to touch on here is going to be economics, right? So it also used in economics. So for economics, suppose you have a function c of x, which is going to be total cost. Total cost. So this is going to be cost function. Okay. So it's a total cost that a company incurs in producing of X units of a certain commodity, right? Some goods, right? X amount of goods. So the function c is the cost function, and if the number of items produced is increased from x1 to x2, let's say, then we can have delta c of x, right? Which would be c of x2 minus c of x1. So again, we can find the rate of change, which is delta c over delta x, which will be equal to c of x2 minus c of x1 over x2 minus x1. Okay, so, and then, right, that would be the average rate, right? Again, average rate. So if we decide to take a limit, so the limit of if delta x approaches 0 is going to be instantaneous rate of change of cost with respect to the number of items produced, is x, right? So, but we actually call it a marginal cost, right? So marginal cost is going to be a limit of delta x approaches 0 of delta c over delta x, which is going to be the derivative of a cost function. Right. So that's something you learn in business calculus. Okay. So essentially, we can we give it a cost function, right? We can find a marginal cost, and we can also find the revenue cost and everything, right? So essentially, there's plenty of applications of calculus. And as we're going to move forward, we will have a lot of applicational problems for this rate of change. All right. Thank you, students, and I will see you all next time.